Okay, this is a review of the final for winter 2020. So one of the questions on the final was not used, and we'll get to it. So this is version 8 winds up, and so yes, this is your version. So report the following arithmetic to the correct number of sig figs. Okay, so let's figure this out. We can break this into blocks and try to figure out what we need. And let's start from left to right. And we'll start within, remember you got to do order of operations. So let's start inside the brackets and then in the parentheses. So here we have some division. So we have what, 1, 2, 3, 4, 5, 6, 7, 8. Sig figs up top. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 sig figs on the bottom, which means this whole unit together will have 8 sig figs. And that relates to this number here. So 1, 2, 3, 4, 5, 6, 7, 8. So that will be the limit for the number on the left. We're then going to add it to this number. First thing we have to do is add these two on the top. So let's add those two together. They both have the same precision to the second decimal place. So let's take a look at that. Here it is right here. So yes, second decimal place is correct. And it winds up 7 and 3. It goes to 10. So this winds up having 5 decimal places and going right to the second decimal place for precision. We can do that subtraction addition together. When we do that, when you add this to this, remember you're going to be limited by the largest error, and that's going to be the second decimal place. So this is those brackets, and that's limited by that second decimal place. Okay, so these two are that number. So we have a logarithm of 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 7 numbers, which means it'll be 1, 2, 3, 4, 5, 6, 7. So it'll be way out here. Now I have to take this number and subtract that number. This has multiple decimal places. Remember, this one is limited by the second decimal place. So once again, the second decimal place wins, right? And that will give us our answer to the second decimal place. Okay, same thing. We can do this one all at once. You don't have to break it down. You can do the 2 on the top and then include the 1 on the bottom. But because it's all one operation, we can include it all together. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So all together, this has 6 sig figs, and it looks like this. 1, 2, 3, 4, 5, 6. So that's where we are on that one. Then this one altogether is, well, just it itself, right? It goes out to 1, 2, 3, 4, the 5th decimal place. So 1, 2, let's see. So we're both here at the 5th decimal place between those two. So this and this have the same precision. And then we're doing the log of 6,300. Well, that has 4 decimal places, right? Or 4 sig figs, which means 4 of the decimal places will be significant. So when we add these together and subtract that, we'll have to the precision to the 5th decimal place, 5th decimal place, and 4th decimal place. 4th decimal place has the largest error, so we'll select the one that's in the 4th decimal place. Boom. For the rule of below, how many significant figures should be reported for the measurement of the bar? Well, let's take a look. What's the measurement of the bar? This will be 1.25. I'm measuring this end. The next one will be 9.5. Okay, good. Let's measure this end. That'll be 1.22. I don't know, I'm going to go 1.9. Right? So let's do that math. 8.15 is a 6. 8.1 is 7. And then a 5 is 3. So 0.0376. That's 3 sig figs. Perfect. Okay, select the definition of significant figures. Select 1. Hopefully we've beaten this into you during the course, but if not, let's do it one more time. All the certain digits that follow the decimal point. I've never said that in class, but okay, probably not this one. All the certain digits plus the first uncertain digit. Pretty sure that's what we keep saying in class, but let's read the rest just to be sure. All the certain digits that precede the decimal point, no. All the certain digits plus 2 uncertain digits, sure, why not? And then all the certain digits and no uncertain digits, that's silly. So, of course, the answer is B. Report the following arithmetic with the correct number of sig figs. Select 1. So on this one, what you want to do is you want to get everything into the thirds power to really figure out what's going on. So let's take our, let's take our first number and put it into the thirds power. That would be 77.294, right? That would be to the third power. Oh, no, wait. Wrong way. Wrong way. So it's a minus 4. So it's going to be 0.77294. Okay, seventh power. So we want to take this one to the third. So let's do it this way. 1.35. This is 7. 6. That's 5. 4. 3. So 0.123. 135. This one is already in the third power. 1.2243. And then this one's the fifth power. Fourth, third, so 0.06834. We can see it's really at this fourth decimal place. Oops, I raised to 2. That wins. It's actually set by this number. So we are going to go with the fourth decimal place. Boom. Student calculates the average and standard deviation for the pressure of a gas of an unknown as this. The dial for the gas meter shown on the right. How should the result be selected? Select 1. Step 1. Does your error begin with a 1 or 2? No, it begins with a 5, so we can keep that. Then we're going to match this. Okay. Rule 3. Are we doing better than the dial? Well, to figure out what the dial is, let's just put a point here and record what it is. Okay. Well, is that bigger or smaller than 700? Yeah, it's smaller. It's bigger than 600. So this is 600. This is 50, or okay, I'm going to say it's 60. The first thing I have to guess at is the 5. I'm going to guess at 665 is that dot, right? Because for the tens place, I have lines, but for the ones place, I don't. So the instrument can only go plus or minus 1. So the best we can do with this is, remember, this is a larger error than that, so we have to go with the ones place. Student calculates the average and standard deviation for pH of an unknown acid is 13.7 blah 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 plus 0.1892. The pH meter shows 2 decimal places. How it should be presented? Rule 1, right? This will be plus or minus 0.19. Rule 2, 13.73. Now, what's the error in the instrument? The error in the instrument is in the second decimal place, so 0.01. What's bigger, 0.119 or 0.01? 1.19 is bigger. Okay, next one. The student calculates the average and standard deviation for an unknown acid is this. The pH meter shows 3 decimal places. How should the result be presented? Okay, it begins with a 1 or 2. Yep, begins with a 2, so we keep 2. That is going to cause it to round up, so it's going to become a 3. So then we keep only 1. So it's in the third decimal place, 1.539. Okay, and so for here, what's bigger? This error or the instrument, which is 0.001? Well, it's definitely the standard deviation is bigger, so it's going to be C. Okay, 10. A student measures the pH of an unknown acid 3 times and obtains the average of this and the standard deviation of that. The pH meter shown below. How should the result be presented? Well, rule 1, yep, begins with a 1, so 0.00015 plus or minus, so 3.7 585. Now the question is, which does this compete with this error, right? Through decimal place. And of course, this is much bigger than the other one. So we're going to go with this is the error, and only one of them have that error. So there you go. An acid has a Ka value of 1.7260 times 10 to the minus fifth. The corresponding pKa is shown on your calculator as this. Report the pKa with the correct number of sig figs. Well, this is a Ka, so this is an equilibrium constant. It's not a logarithm, so we have 1, 2, 3, 4, 5 sig figs. And in a pKa, that's a logarithm, which means we have to have 5 sig figs past the decimal place. 1, 2, 3, 4, 5. Right? Moving on. The pKa of an acid is reported as 3.62. The corresponding Ka shown in your calculator is 2.39 times 10 to the minus fourth. Report the concentration with the correct number of sig figs. This is a pKa. This is a logarithm, which means the sig figs only exist after the decimal point. That means it has 2 sig figs. So we need to find the corresponding Ka that has 2 sig figs. 3, 4, 2. Ah, perfect. Ah. Awesome. Next. A student measures the mass of precipitate for 6 trials using the balance shown below, and calculates the average as this and the sample standard deviation is that. How should the student report the result? Select 1. Okay, well, rule 1, 0.003. Rule 2, 1.822. Rule 3, what's bigger error? 0.01 from the scale, because there's 2 digits, or the 3? Well, it's 0.01 from the scale. There's only 1 here with 0.01, and then, of course, making that match. You measure the volume of 3 titrations with a calibrated NaOH solution using a burette that has precision to the second decimal place. You get the following volumes. You calculate the number of moles of each titration using calculator. The calculation for the first titration and calculator output are as follows. The average number of moles of the sample standard deviation for 3 alquats shows up on your calculator as this. How should you report the error? Step 1. 0.12345. 1, 2, 3, 4, 5, 3. 0.12345. Is that right? 1, 2, 3, 4, 5. We need one more. Okay. Rule 1. Rule 2. Okay. So now, oops, no. We got to figure out the instrument on this. Okay. So we have precision to the second decimal place here. We have a conversion. These are integers, so these do not have sig figs. Right? We have some concentration of NaOH, and we have our molar value. Right? So let's figure this out. Right? And this is all multiplication. So I have 4 sig figs, infinite sig figs. I have 3 sig figs, which means I can only have 3 sig figs. My instrument error is in the 5th decimal place. So my instrument error is 1, 2, 3, 4, 5. 5th decimal place. Okay, so what's bigger, a 1 in the 5th decimal place or 3 in the 6th decimal place? Well, it's definitely this, right? That's a no-go. So we have to make that match, 0, 0, 1. And then we just find it. If you'll notice, it's also the only error, so that you could have just searched the error. Okay, we have the same question below. Some different volumes and a different calculation, but it's the same question as above, just some different numbers. So we're just going to solve it the exact same way. There's nothing special here. First rule, plus or minus 0.1, how many zeros? 1, 2, 3, 4. 1, 2, 3, 4, and a 4. So we have 0.1, 2, 3, 4, and a 2. Okay. Now, where's our error in this calculation? The calculation is the same as above, because look at the first one is the same as that number. Oh, geez, someone's lazy. Couldn't be me, could it? Yeah. 4 sig figs, right? Conversion infinite, 3 sig figs. So once again, we're going to be out here. 1, 2, 3 sig figs. We're going to be in the 5th decimal place. 0.1, 2, 3, 4, 5 is our instrument. So what's bigger? In a 1 in the 5th decimal place or a 4 in the 5th decimal place? Well, 4 in the 5th decimal place is definitely bigger. So, C. Student measures the mass of precipitate using 3 different balances showing here. The records are shown as this. The average is calculated from the calculators given. Report the average. Now, the key to this is grams, this is grams, this is grams, and the answer is grams. So unlike the previous ones where we're actually looking at propagation of error through different units, we're only looking through grams. And what's really going to limit our grams, right, is the scale that's in the second decimal place. This is like taking the average of 3 bank accounts. If one of these bank accounts has a large error in it, no matter how well you know the other ones, you can't win. So it's this 2 decimal places that sets this entire calculation because we're still in grams. Okay? And it's addition, right? You buy 2 identical balances and use them to measure the mass of the same beaker. The mass is measured 4 times, and the average and standard deviation are calculated. Balance A is 20 with 2 significant figures, plus or minus 4 grams. And balance B is 40 with 2 significant figures, plus or minus 8. The beaker is known to be exactly 30 grams. Select one. Okay. So, precision. Okay. Which is more precise, right? They're both equally distant. They both have the same precision, right? They're both really in that second decimal place. Right? So they both have relatively the same precision. Right? Neither of these is really more precise, right? Because how do you measure precision? Right? You have to calculate the RSD. So the RSD for balance A is 4 over 20, which equals 1 over 5. And the RSD for balance B, this is for balance A, balance B is 8 over 40, which also is 1 over 5. So they have the identical precision. C, precision cannot be determined because neither balance is accurate. No, that's not true. You can determine the precision. We just did. More measurements will increase the accuracy of both these balances. No, this is stupid and made up. More measurements just let you know the statistics better. Won't increase accuracy. So the real answer for E is E. None of these is correct. So hopefully you can see that neither is more precise, even though maybe one looks more precise. You really have to compare that RSD, and it's just a simple measurement. Okay. 18. Select 2 false statements. Okay. Random error shift results in both directions. True. Systematic errors in theory can be identified. True. Systematic errors always have a Gaussian distribution. False, right? That's random errors. Repetition of measurements will reveal systematic error. No, you can measure something with a tape measure that's too short all the time and you'll never find that out. So false. Random errors can be made smaller by using different instruments with higher precision. No, all right, the random errors cannot be made smaller that way. I'm sorry, that is true. Random errors can be made smaller, right? If you're going to get a new instrument that has higher precision, like a better pipette, that is, I'm sorry, absolutely true. I'm tired. After 34 trials, the average mass delivered from a pipette is 100 grams. With a standard deviation of 5 grams. If you perform the 35th trial, what is the probability the mass will be between 95 grams and 110 grams? Okay, there's 2 ways to solve this. I'll show you the mathematical way, and then the way you should have solved this with intuition that's maybe a little bit better. So if I have a standard curve here, and my average is at 100, I want to know between 95, which is 1 standard deviation, and I want to know to 110, which is 2 standard deviations. So I can either take, right, 1 standard deviation is 68, and that's half of it. This one is 95, and I'm going to take half of that. So half of 68 is what, 34? Half of 95 is 45, 46, 47 and a half. 7, 8, 9, 10, 11 is 81.5. So mathematically, that's the area under the curve, and you get this. Okay, let's find a different way to do this. Less math. Okay, so here let's go back to, we have 1 sigma on the left, and we have 2 sigmas on the right. So 1 sigma to be under 1 sigma has to be 68. Well, this is more than 68. 2 sigmas is 95. It has to be less than 95. It has to be neither of these values, but somewhere in between. So it can't be that value or that value, so it has to be somewhere in between. All right, so you could do it without math as well, just a little bit of logic. Select a true statement about RSD. Select 1. Okay. More than one of the other statements is true. Okay, we'll come back to that one. The sample RSD equals the population RSD when the sample average equals the population average. Okay, no, right? The population, the sample RSD does approach or equal the population RSD when n approaches big N, because both mu, because both the average approaches mu and S approaches sigma. And remember, RSD is simply X bar over sigma. Actually the inverse, I'm sorry. Right? So if these two approach it, then RSD also approaches it, but only when N approaches this. The population average equals the, remember, you can go over that multiple times. Remember in class when I had all the people that were 5'8" stand up, and I'm like, oh, hey, look, our average is the population average. Well, that's just based on a small sample, or during the sampling something has occurred, right? This only holds true when N approaches large N. Okay, and if you don't understand this, you should come to help room or come visit me. So, negative. Okay. None of the other statements in this question are correct. Okay, we'll come back to that. The sample RSD approaches the percent error when the sample size approaches the population size. Wow, that sounds good because we're talking sample size approaches population size, but the fact that I'm mixing RSD approaches percent error, I'm mixing precision and accuracy. That does not make sense. The sample RSD provides information about the accuracy of the measurements. Once again, RSD is precision, not accuracy, so absolutely none of these. So more than one can't be true, so none of the above statements are correct. Number 21. How should you report an average and its corresponding standard deviation? Select one. The average and standard deviation should have the same number of significant figures and the same number of decimal places. Absolutely wrong, right? We really only want to report that to 1 or 2. The error is only reported to 1 or 2 significant figures, right? So if you have something that's more than that, this one holds. The average should be reported to 1 significant figure unless it begins with a 1 or 2, then it should be reported to 2. This would be correct if it wasn't the average, it was the error, right? So I swapped out a word on you there. The average should be reported to the same number of different decimal places, precision, as the standard deviation. Yeah, so if your standard deviation is 0.03, then your average should be reported to that same precision. That is true. The average and standard deviation should have the same number of significant figures. That's just crazy, right? Your error should only have 1 or 2. And then this one is true, so that is not true. So the answer is C. Select the 2 true statements. The percent error provides information on the relative accuracy of one measurement to another measurement. Percent error does provide information on the relative accuracy from one measurement to another measurement. So that's how you compare the 2 pipettes or something together. Repetition of a measurement will reveal the size of the systematic error. No, it will reveal the size of the random error, right? So that will be a big old false. Systematic error is revealed with the repetition of measurements. No, once again, this is random error is revealed with that, so false. Systematic errors can be compared by calculating their percent errors. Yes, Accuracy can be compared with the method to compare accuracy. True. Systematic errors reflect statistical fluctuations associated with the measurement. No, this is false, right? That's random error. So this one, I meant to come back and change one of the answers. So there was no, it was supposed to say none of the answers are correct. So this one was not used on your exam to grade it. I didn't get back to it. I totally spaced it. And so everyone got the points. Yay. 24. What's the correct reading for the Burette on the right? Well, let's see. This is going to be 632. Right? We have decimal place that is, I don't know, we'll go 7 and then maybe a 1, right? Because the decimal places, right, there's a 0.1, 0.2, 0.3 have a line. So that's certain. And then the first place I don't have a line for, that's uncertain, is that one, right? So it'll be E. You buy new tires for your car. The technician calibrates your speedometer to your new tires. After months of driving, the tires become worn. The diameter of the tire gets smaller. Select one. Okay, so what happens if the tire gets smaller? Well, for some given distance, it's going to spin more, right? So if you're going at some velocity, it has to spin more over that distance, so it'll make your velocity always appear faster and faster. If you get this wrong, you could say, oh, even if you go the wrong way, it'll get slower and slower, right? So it's only going one direction. It's not going to get slower, faster, slower, faster. So we should know that this is a systematic error, right? So let's take a look. This increases the random error on the speed of the speedometer. No, right? It's systematic. This increases the precision of the speedometer. Once again, precision deals with the random error. This decreases the precision on the speedometer. Once again, that deals with random error. This creates a systematic error on the speed reported by the speedometer. Absolutely true. The variance of the speedometer will always be 0. We never talked about variance in the class. So the answer is D.